Hi, and welcome to another exciting edition of game shading techniques and training theory. My name is Nate Nestler, and this is for Hyperactive Studios. Okay, so real quick here, let's do a quick breakdown of this. This will all make sense. So say you have an image like this, a texture, for instance. This is a texture. And you were to get a sample of it, and say you're looking at a single pixel, and you have the surrounding pixels around it. And this would be what's considered a 3x3. And this is your center pixel that you're looking at. You could sample the surrounding pixels around it and do what's called a filtering technique. And this will allow you to blur these other pixels and all kinds of fun stuff with it. And you can also use this for edge detection. You can use it for oh gosh, so many things. You can use it for bloom, you can use it for glow, you can use it for blurring, you can use it for shadow blurs techniques, for blending things. You can use it for basically animated cartoon-like looking drawings techniques. You can do so many things. I'm not even going to bother going over it. All the stuff you can do with this filtering techniques, tons of stuff. It's really important. It's used for a whole lot of stuff, and we definitely need to talk about it. Okay, so say we were to access this. Let's look at how we can actually go about accessing these different pixels so that we can do one of these techniques. So I'm going to go ahead and pull this up here, and I've colorized these pixels. So the way these work here is you have different weights you can have applied to each pixel on here, and the centermost pixel is going to have the most weight. And so typically, almost always, you can do different shapes though with this weighting. So this is cool. Once you have these weights set up like this, you can just manipulate them to do, say you want to do a cross filter, or you just want to do a circular filter where you have the centermost points the strongest. Same thing in the cross too. Centermost points the strongest, and then your outer ones here are evenly weak all the way around. Whereas a cross one would be, these would be stronger, and these would be the weakest points here, and then these 4 points would be the next most strongest, and then this would be the strongest point of all for weighting. And in this way you can say that this point doesn't matter as much as this point here for blending the colors, for your averaging. And that's great because then that prevents you from blurring this one out too much and not having as much influence as it should and lose too much detail. So this is great because it prevents you from losing too much detail with these weights. As you can see though, it's in a basic grid layout here. So 0, 0 is going to be your first pixel here in the corner, and 2, 2 is going to be down here at the bottom. Whereas 1, 1 is going to be the center point, and it's typically going to be your highest weight. It's at the center of weight 11. So that's basically how it works as far as that goes, for how you would access these pixels around your surrounding pixel that you're trying to modify and create blur. Realize that we're computing this in a GPU. So we're doing massively multi-threaded computations. So this means every time we're sampling one of these pixels, we're doing how many computations, guys? 9 computations. That's right, 9 pixels here. So yeah, every time we grab one of these pixels, we have to grab the surrounding pixels around it so that they can be weighted and averaged, and so we can get our final blur point here, or glow point, or whatever, in the center, where we decide we're going to do with our filtering, for that matter. All right. And then you have your weights over here on the other side, on the left, here showing you how those can be weighed out, and basically which ones you would access for that. So let's look at some code, and let's not forget that this is a highly parallel problem, so we don't have to worry about if condition statement branching or anything like that. Instead, this is all computations that can easily be broken off into their own little parts in the kernel of the GPU for being processed with the memory, and it can be computed very quickly, very fast, and high speeds, and they can all be computed independently of each other. And that's a very important key point here with massively multi-threaded computations. They need to be independent calculations where they can be computed independently of each other. They don't rely on each other to be computed, and thus allowing it to be computed much faster. So each one of these is going to get computed 9 times per pixel, so it's quite a bit of image access. This would be very slow on the CPU. This is why we want to do it on the GPU, because it makes it run so much faster. It's way, way faster. This right now is what's called a box method, though, for filtering. There are other types of methods, like Lanczos, Gaussian. There's also Mitchell. Those 3 are my favorites by far. Lanczos and Mitchell are my 2 favorites of all, but Gauss gives you a nice blur if you're trying to get a blur effect out of it. So there's different types of filtering techniques, And you know, the box one's the fastest one. We are doing a 3x3, so it's way better than a 1x1. 1x1 would just be the pixel. This is a 3x3 because it's 3 pixels over and 3 pixels down. You know, so this is a 3x3. As you can see, 3 this way, 3 that way. So it gives you a total of 9 pixels when you do a 3x3. Some will see 4x4s, 5x5s, and 6x6s. It's about as big as I've seen is a 6x6. But realize you can do that. Okay, so with that said, let's look at our filtering here, code for the techniques. All right, so this is like a pseudocode, and this is just, let me go ahead and just break this down like this so we can explain it and how it works. Okay, cool. So if I have my pixel and my UVs, I subtract a step vertical, and you're going, well, that was going to move it down, right? Yeah, I was kind of thinking that way, but no. Think about it for a second. Your 0, 0 is up here, right? And 1, 1 is down here. So subtracting, it's literally going to move it up instead of down. So this is totally right. You have to think backwards. This is not the way you're thinking. You're normally thinking what? You're thinking in your Cartesian coordinates, right? You're thinking, oh, well, positive's always going to go up, right? Not in this case, because 0, 0 is at the top here in the corner, and 1, 1's here at the bottom. So by subtracting, we move up, and by adding, we move down. By adding, we move over, and by subtracting, we move this way. So does that make sense? Because remember, 0's on this side, right? So if we subtract, we move this way. If we add, we move that way. So our Cartesian coordinates are the same as what we have for our UV coordinates. They lay out the same for horizontal. They lay out totally opposite of each other, inverse of each other vertically, because again, 0 is at the top and then 1 here's at the bottom. So if you think of this as fourth quadrant of your Cartesian coordinate system, over here the bottom coordinate quadrant, that's what this would be as far as the UVs are laid out, as far as that goes, and the 0 to 1 relationship. So that means that if we say the UVs here subtract step vertical, that's going to do what? Remember, 0's up here, so if you subtract from it, it's going to move us upward. So we move up, right? Subtract step horizontal is going to be, wait, what? 0, 0. So check it out. Color 0, 0 here. Pixel minus step horizontal. Okay, cool. Now we need to compute the one. Now we've already done what? A vertical step. So we're up here the whole time, all right, for all these computations. And then for what? Weight, color, 01. Yeah, so 01 here, we're setting the pixel to it. Awesome. For weight 02 here, now I'm saying weight here, but honestly these are just colors that we're pulling the actual pixels. So we're grabbing the pixels right now for the sampling. So we're grabbing the pixels from the sampling from the actual 3D card, from the texture sampling from the texture space memory on the 3D card, and we're accessing these different points in memory. Okay, and that's how we're doing that right now. We're actually moving ourselves through the memory accessory function capability there within inside this shader called sampler, a texture sampler. Alright, so here we're going to move over to the right, and this is going to be our pixel step horizontal. So yes, we're going to move over 1. So that adding that one amount of space we move over, and I say step horizontal because it could be maybe we skip a pixel or something like that. Sometimes we do that, and we get better blurring effects or such. So I've seen other techniques where they well, screen space ambient occlusion is a good example of this, where they want to skip a pixel and then thus blurs across it, and you get a better result because you get a better softening of the pixels than doing the one very next right next to it. So interesting, very interesting, and then in doing so you end up getting a smoother result, believe it or not. I know that sounds crazy, but usually the reason they have for that is because saying that, so you can actually swap this up and change things around a bit on this. The reason why they were saying that is because you gotta realize the pixels right next to the one you're sampling are typically very close to the one you're sampling. So if you're wanting to get a lot more blurring or a lot more variation, reduction of variation, then you're going to do a larger step size to the left or right. So that's why I'm saying that's what the step horizontal is, not necessarily just 1 to the right, but in our case, in this example, it is 1 to the right or 1 to the left, so on and so forth. In this case, we have pixel step horizontal. It's going to go to our right. All right. And then we have our, now we're going to do our vertical placement again here. So for pixels, UV, so where does that place us back at? Our pixel, our original pixel here. Okay, so it places us along this row here. So we're going to step horizontal to what? The left, because we subtracted from it. Okay, cool. So it gives us our pixel to the left, and then we're going to say pixel here. It's going to give us our actual pixel, and that's going to go into color 11. So check it out, matches with 11 position, with 10 position, so on and so forth. All right, and then position number 12, how do we get there? Well, that's simple. We just add a step over from that pixel there. Okay, cool. And then we need to do what? We need to move down here and compute these. So again, remember, this is 0 to 1 type relationship. So 0, 0 is here, 1, 1 is here. So we have to add to move down. So that's what we're going to do. We're going to add to move down. So UV step vertical here. We're going to move down like that. And then we're going to subtract our pixel from our step horizontal to move us over here to the left. So here in this way, we get over to our left, and we sample this pixel here. Pixel here is just going to move us right here, and we're going to sample it because remember, we are already moved down for this whole row of pixels here from previously, okay, on our UVs. So we're going to sample this pixel now here, and then if we add one step horizontal over to the right here by adding it, it's going to move us to 2, 2. So that gives us color 2, 2. Now cool, check it out. Our weights are going to correspond with our pixels. Imagine that for the colors. And then thus, when we sit there and take our color here, 0, 0, we multiply it times what we decide we want to be the weight for the 0, 0 pixel, for how important we feel it is, it's going to determine the final value of this color. So how much contribution does it do when we add them all together? It's essentially the case. And so all our different weights determine how much of contribution these different colors that we sampled from the surrounding pixels around our core main pixel here. And thus doing so, we end up with our final computed color here at the very end, because we just add these up as we go all the way down, and this is with all combined. So then we have to say the total number of elements. In this case it's 9, because we have 9 pixels that are sampled, right? 3 by 3, so this would be 9. If this was a 4 by 4, it'd be what? 16. 5 by 5, 25. 6 by 6, 36, so on and so forth. In this case it's a 3 by 3, so it's going to be 9 elements in here. And we're going to divide it by 9, so that way we get our final color for our pixel, our final pixel, the result there. And we say equals final pixel, and then that gives us our final pixel. And in doing so, you would get something like a box method like this right here, and which is a glow shader as a good example of it, okay? So that's a good example of a glow shader right there. And that is essentially how it works. And that is how you can do box method algorithm. This is a very important algorithm. It is something we will use quite a bit, and it's something you absolutely need to know how to do for many techniques and many methods. And this is essentially how it works, and this is the mechanics behind it. So when you see them talking about these glows or blur, and a lot of times they won't even tell you the daggone code or anything of the sort, or how they're breaking it down, or where this came from, or whatever. This is where it came from. It's this filtering techniques. This is what happened. And they've been around for a long time on the CPU side, but they're kind of slow when you're computing it on the CPU, and thus moving it over to the GPU has caused a major increase in speed for calculations. So we're talking it's way, way faster. The GPU is really well designed for handling textures and images and computing them super fast. So they've designed the actual hardware to handle it and do that precisely. So this kind of techniques really do need to be done on the GPU side, and I think you'll get a much better result in doing so. But with that, that covers this basic technique and method. And if you want more details on this, I would have to recommend a particular book that goes over this in far more detail than I ever did, and in far more depth. It doesn't break it down in an easy to understand method like this, but once you see this broken down like this from what I presented here, I think you'll find the book a lot easier to understand. But if you look at the GPU Gems book from NVIDIA, the first book there, they have a chapter in there that's really cool, and it's called High Quality Filtering. So I can't remember what chapter that is. It's chapter 24. Okay, so chapter 24 it is. So check that out in that book, and after seeing this, it should make a lot more sense as to where the code's coming from and what's happening. And that really helps break it down, because they don't really go over this at all in the book. And I want you to see this and understand this, so you understand what's happening here in our code later on and everything. And if you want to see more details on this, a lot of different types of techniques and things like that, go check it out in the book. I might go over Gauss, Lankos, and Mitchell later on. Please check out that chapter. It is more techy, but it is a very nice presentation of filtering techniques, and I think it's definitely a worthwhile view. I definitely love bringing out other people's training materials that are excellent out in the field, and whenever it's useful. Unfortunately, most of them don't show an actual implementation of how to actually pull off something from start to finish. They assume you already know a bunch of stuff. So the point of my training series, for the most part, is to show you how to actually put something together and actually make it work from start to finish. And then when you look at these other training materials and stuff like that, they'll just make sense to you because you've already been working with this stuff previously, and it won't be suddenly, I have no idea how to do this, how to go about it. So now with this training series, with you going through it, you will have a good understanding of it. And then when you look at other training resources, you can actually make sense of them. So that was the whole point of it. Came out of a matter of a necessity and need that I've had with my students, and it's just been an issue with a lot of the training materials don't actually cover how to actually pull something off. So with that, my name is Nate Nessler, and that covers these texturing filtering techniques. High quality filtering. Well, this isn't real high quality filtering with box method, but you get the idea. It is a filtering technique, and it's not bad. It's not bad. A 3x3 gives you good results. But anyways, it is faster to do a 3x3 box, by the way, than it is to do a Gauss, Mitchell, or Lankos. So it is faster. It's not as pretty, but it is faster. So we're going to go with the one that's faster for now, and simpler too. Which is great at first here. We might get into the more difficult stuff later on that. Okay, now we were just talking about doing the whole glow part of the theory, and let's move into actually how to code this shader. Now, you probably want to base this off of your radial blur shader from before. This is a screen space effect, and we're going to take that filtering theory and we're going to make use of it. So, how do we do that? Well, quite frankly, it's not that bad. We're just going to say create, and in effect, choose CG, say next, say empty, call this screen space glow, please, just like up in here. And yeah, name that right here. And then copy and paste in your radial blur from before. And you should have it. Go ahead and put this in your project with your screen space shaders into the same project as that. So that way it's with all your screen space shaders, because this is a screen space shader technique. Now the cool thing about this is this could also be used with your deferred shader pipeline that we were doing previously if you wanted to. Anything of that nature. Right now we're just keeping it simple by just doing these simple screen space shader techniques separately. But you can pack these right into your deferred shading and then manipulate your final results of your deferred shading and lighting further with this as your post-process technique at the end. So that's really cool. Allows a lot of flexibility and a lot of capabilities, and just makes it where you can process your whole scene a lot faster and easier. Anyways, that's one method of doing it. Of course, you could also do the object by object shader method too and use this with it. So in order to keep it extrapolated from a particular setup or whatnot, we're just doing this as a regular screen space shader as post process, and then you can decide whether or not you want to use this in a deferred shading pipeline, or if you want to do this on an object by object shader process model pipeline. So it's totally up to you how you want to go about it, but both methods have been presented. I coded this a little while ago, just now making the video on it, so this is months ago. I had to go back over the code to remember what it did and such back when, but regardless, we have a whole bunch of, well, the theory directly ties into this, and let's just go over this. So first off, put up your comments, make it look professional like this. We're kind of staying with that for now. And then we're going to go in here in a script, standard global here. Of course, UI widget equals none, in quotes. This is all the same from before of your radial blur. So if you did your radial blur, copy and paste in here, there should be nothing different. String script class equals scene, in quotes, semicolon. And then we have our string script order equals post process, close quotes, semicolon. String script output equals, in quotes, color here, close quotes, semicolon. And then string script equals technique 0, semicolon, close quotes, semicolon. And then close greater than sign equals 0.8, semicolon. All right, let's get to the actual meat of this. So now we set up our post process, and this is going to be processed for the scene. And it's going to be a screen space technique, basically, because we're handling the whole scene, so therefore it's screen space. Now I'm going to go ahead and just pull this out. Real quick, though, you can see, okay, well, first off, let me show this off a bit. Before I start running off into the code, I should probably show some things off. Alright, so what's happening? Here's the original render. Okay, so this is what we get from our original render, as it's done by the regular setup here. And then we're blurring it horizontally, and then we're blurring it vertically, or yeah, I think that's the order. Maybe it's the other way around. And then this is our depth value here. That's just showing. So I can zoom in and out, and to cause my glow. And the glow is based on the depth, so you can see the results of that. But essentially, that's what's going on. And I can go in here and I can increase my glow strength, like so. As you can see, very cool. Down to practically nothing at all. But I don't know, 0.6 was nice. The other thing we could do is increase our scene strength. Overall brightening of our scene. It's just a multiplier. It's simple. Not a big deal. Okay, something like that maybe. Glow step size. Alright, so how far does those textiles extend out? You see it looks like the glow effect has just dropped off all of a sudden, and then now it looks like it's blurring out and glowing more and more and getting hazier and hazier. As we go higher and higher, though, you can start to see the textiles appear. That is the downside of this technique. We just literally run out of data to work with that would keep it smooth. So you start introducing textiles or distortion loss here when you start going too far with this method. So be aware of that. We are using the box method, so that is a artifact of the box method quite commonly. You do tend to get box-like, that's not why it's called the box method, but you get box-like artifacts from the box method. Gaussian is going to give you a much better result. We're not using Gaussian for now. Baby steps. Absolutely baby steps. Here we can change our viewport offset. I'm not changing that. And then here we have our generated textures. Now, of course, I could make these not appear in here at all if I was so desired. But for now, as it is, there we are. Okay. So with all that said, now I'm going to expand out the screen so that we have room for code. Alright, and then some actually. Well, since I have so much room, let me pull that back a bit here. I wasn't expecting to have that much room. Ended up being a good bit more than I expected, so let me just move that back a little bit. Let me enlarge this code a little bit. Should make it a little easier for everybody to read. Alright. Now the code's bigger and easier to read. Alright. So with that all said, let's move on here with this. Now I'm just going to go ahead and scroll down in here. We're going to look at the image filter weight. So how does this work? Well, basically this is your actual main pixel that we're sampling. So this is the original pixel, if you will, or textile if you want to put it that way. Textile, remember, is an uncomputed pixel here. Or okay, sorry, textile, texture, pixel. It can also be referred to as a fragment if you want to talk about uncomputed pixels. But essentially, yeah, that's what we're talking about. We're talking about a pixel on the screen, and we're going to manipulate it. So this particular pixel here is the original pixel that we first read in. This is the actual pixel in question that we're modifying. Alright, and this means 0 distance from the original pixel. So that's why it's 0 here. Weight 0 for the original pixel. And then weight 1 is going to be 1 pixel out from the original. So let me just pull up real quick a little graphical here to show you what I'm talking about. This would be your original pixel, the one in the center. So that'd be your WT underscore 0. It'd be like your weight 0. And then weight underscore 1 would be 1 pixel out. See that? So these are all 1 pixel away from the original one. Then weight underscore 2, we're going even further, would be 2 pixels, would be the second pixel out here in a much bigger region of image that we were sampling here, going out in this area. So it'd be 2 pixels away from the original center one. Weight 3 would be 1, 2, 3 pixels away from the original one. So you start to get the idea. So it's further and further away. And then weight 4 would be 1, 2, 3, 4 pixels away. So we're really talking it's getting far away from the original one. So for this reason, we don't want the pixels that are really far away, like 4 pixels away for instance, having a strong influence or weight over the original pixel. If it does, the problem we'll have is that the original one will get blurred out a lot more in doing that. I mean, you want to retain some of the detail of the original one, and the further we go out, we want to have less and less influence over the original pixel. Otherwise, we're going to retain very little of the original detail at all if we don't do that. So, and that's the reason why. So you can see the original pixel has a weight of 1.0, which is full weighting. The very next pixel next to it has a weight of 0.9, which is pretty high. And then 2 pixels away, its weight is 0.55. And then 3 pixels away is the weight of 0.18. And then 4 pixels away only has a 0.10 strength. So that's quite a small amount of weight compared to, say, the actual pixel or the one next to it, etc. When you reach the 4 pixels away. So because of that, that does make it where we're taking less and less influence of the data as we go further and further away from the main weight here. Now you can change these points up based on the way this is coded. You can change these up, and by changing these values you can get different interesting effects occur for the look of things as far as that goes. Okay, and then in the next part here, we're going to normalize or create a normalized average weighting of this. What this allows us to do is to avoid having to do this whole process here at the very end here where we have to divide a final pixel by color weighted divided by total number of elements. That eliminates that whole need because we basically bring this back into a 0 to 1 relationship here with all these weights here. So it breaks it back down to a 0 to 1 relationship, and then when we use it throughout this here for calculating these weights, we'll end up getting a 1.0 result, so therefore there's no need to divide. This is a little fancier method for handling this, but it works and does the same thing. This will prevent it from having to either darken or brighten, because what happens if you multiply a color times 0.5, right? It gets half as bright. You multiply, and if you add 2 to it, then it's going to get double as bright. I mean, it's going to get way brighter, you know, as far as that goes. If you multiply it times something above 1, like to 2, it's going to double the brightness. So that's what we're trying to avoid here. And of course, if you're adding again, that will be increasing the brightness. And if you over divide, you're going to be darkening it. So we don't want that to happen. So what we do is we simply just divide by the amount that's inputted, so we get back to an original value of 0 to 1 for the color range. And that's essentially what we're doing here. So we're bringing it back to a brightness level of 0 to 1 for the color range, but we're still taking in an influence of all of these different weights. So the final weighting is a 0 to 1 range here by doing this. So that's ideal. and that makes things pretty cool. We have this define command where we're actually defining a variable as a constant in here, and that's pretty cool because we can turn around and use this later on in our program. Alright, so here we have our weight 0, or shall we say our original pixel. Alright, it has a weight of 0, weight underscore 0 here. Weight 0, remember, had that weight of 1, but then it gets divided by our normalized weighted value here, normalized weighted average, if you will. And, well, okay, it's not an average yet. After it gets divided, it becomes averaged. Here we're adding them all together. So we're adding them all together first, and then when we divide, we get our average. So we're generating a normalized weighted average. Let's put it that way. And so here we are creating that. Yes. All right, and then we do that for each weight as it goes off into the distance. And remember, each one's going to have a decreasing value. So this just brings it back into range, essentially, by dividing it this way. And in doing so, we no longer have to worry about that final divide at the end of the code. So that makes life a lot easier. So now we've brought everything into our range of 0 to 1. So all these should be able to add up to 1, I believe, if I'm not mistaken, 1.0. Okay, let's move on down. Again, in order to do this, just copy and paste and then change your numbers. 0, 1, 2, 3, 4. Again, 0, 1, 2, 3, 4. So on and so forth. Nothing mystical there or whatnot. And that should give us our weights. Alright. Now, let's add some glow. So here's going to be our glow strength. Let's call it glowness. Could call it glow strength if you like. I don't care. And here we have our UI name equals glow strength. And then UI widget equals slider, in quotes. UI min equals 0.0 f, semicolon. Float UI max equals 2.0 f, semicolon. Float UI step equals 0.05 f, semicolon. Greater than symbol equals 0.7 f, semicolon. Float sceenness, open greater than sign here. String UI name equals, in quotes, scene space strength, close quote, semicolon. String UI widget equals, in quotes, slider, semicolon. Float UI min equals 0.0 f, semicolon. Float UI max equals 2.0 f, semicolon. Float UI step equals 0.05 f, semicolon. Close greater than symbol equals 0.3 f. Now, if you remember right, glow strength makes it glow brighter, and seenness here, or scene strength, is going to brighten up the whole scene, or darken it, depending on how you go with this whole value. Once you go under 1.0, you're going to start making the scene darker. If you start going above 1.0, it's going to make the scene bright. So you can make it totally dark or double as bright for scene. Same thing goes for glow. Alright. Glow span here. How much of a step size do we take for our texels for manipulating it? Alright. So greater than symbol here, string UI name equals glow step size, open parentheses, texels, close parentheses, close quotes, semicolon here. String UI widget equals slider, in quotes, and then semicolon. Float UI min equals 0.2 f, semicolon. Float UI max is equal to 8.0 f, semicolon, and then float UI step is equal to 0.5 f, semicolon, and that's greater symbol equals 2.5 f, semicolon. Alright, and we need to do our clear color as always. So we have float 4 here, clear color, and then open less than symbol, and then string UI widget equals, in quotes, none, close quotes, semicolon. Close greater than symbol equals, in curly brace, 0, 0, 0, 0, 0, close curly brace, semicolon. And again, this is totally black. And let's not to mention, we can also put const in front of these, because these are constants. These are not. These are uniform types, and they don't have to be varying variables. So remember, that saves us on our GPU. It cuts down on what they have to do on processing here on the card, and thus makes it run faster. And I keep forgetting to do this. So anytime you have these uniforms, don't forget to put const in front of them, because it will save you time. Alright. And I believe I should be able to get away with this for each one of these two. Alrighty. Jiminy Christmas. Yep, no problem. Oh, I ended up doing const twice. My mistake. Thank you. Alright, my mistake. Alright, so glow span, again, this tells how many pixels away are we going to be when we sample it. And that's what we're determining here. Just how far out we go with that. So const float glow span here, less than sign, string UI name equals, in quotes, glow step size in textiles, close quotes, semicolon, string UI widget equals slider, open close quotes, semicolon, float UI min equals 0.2 f, semicolon, float UI max equals 8.0 f, semicolon, float UI step equals 0.5 f, semicolon, or a half a pixel, close greater than sign, and we default it to equaling 2.5 f, semicolon. So we had our const clear color here. We have our, sorry, I already did this. Const float clear depth here. Open less than sign string UI widget equals, in quotes, none, close quotes, semicolon, greater than simple equals 1.0, semicolon. And then const float to viewport size for our viewport, colon here, viewport pixel size, yay, open less than sign string space UI name equals, in quotes, screen size, close quotes, semicolon, string UI widget equals, in quotes, none, close quotes, semicolon, and then close greater than sign, semicolon. So there we are, we define that. And then we have const float to viewports offset equals float to here, and we have no offset at all. So it's 0.0, comma 0.0, close parenthesis, semicolon. Alright. Now, with that all said and done, let's hit up our texture screen space texture. Rendering color target, or shall we say what goes through the screen. Alright. So our screen space texture is going to be the same as from before. We shouldn't have to change anything here, but let's go through it anyways. Texture screen space texture here, colon, render color target, open less than sign, float, okay, that's nice. Windows, go away. So float to viewport ratio equals curly brace 1.0, comma 1.0, close curly brace, semicolon, int MIP levels equals 1, semicolon, because we're only dealing with our own 1 MIP level. String format equals, in quotes, x8, r8, g8, b8, close quotes, close semicolon. And by that, I'm saying MIP levels. We don't have multiple MIP levels. We only have one MIP level, which is to say the actual image itself. Because it's a screen, we're not moving back and forth in depth. We only need one MIP level. String UI name equals, in quotes here, I do this every time, screen space 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 texture. When I'm saying space, I mean the actual space here in between. So screen space texture here, close quotes, semicolon, string UI widget equals set of quotes here. Alright. Sampler 2D here, screen space sampler equals sampler underscore state, texture equals, imagine that, screen space texture. Yep. Close greater than sign, semicolon. Mag filter equals linear, semicolon. Min filter equals linear, semicolon. MIP filter equals point, semicolon. Wrap S equals clamp to edge, semicolon. Wrap T equals clamp to edge, semicolon. Close curly brace, semicolon. Texture screen space glow horizontal, colon, render color target, open less than sign, float to viewport ratio equals curly brace here 1.0 comma 1.0 close curly brace semicolon, int mip levels equals 1 semicolon, string format equals x8 r8 g8 b8 close quote semicolon, string UI name equals in quotes screen space glow 1 texture close quote semicolon, and then we have string UI widget equals in quotes close quote semicolon close curly brace, not curly brace, close greater than symbol semicolon. That finishes this video. And my name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.